Hello everyone, I'm Tanmoya Ghosh and today I am delivering a lecture video on discrete time signals and systems. Okay, so what do we mean by a discrete time signal is first we will see. So a discrete time signal is nothing but which is defined only at discrete values of time or some other appropriate variables, for example, space. Okay, so how does it look like? A discrete time signal will look like this. That means my time value is discrete in nature. It is having a specific values at -3, -2, -1, 0, 1, 2, 3, 4. So the amplitude value can be continuous in nature or else it can be discrete in nature. So a discrete time signal's amplitude can be continuous or it can be what? It can be discrete. But the time value will be always discrete. So these are the 2 points to keep in mind when we are talking about discrete time signal. So how do we get this discrete time signal? Because everything in nature is continuous. Okay, the voice signal or the audio signal of whatever I'm speaking right now is also continuous. Everything in nature is continuous. So suppose I have a audio signal like this. So I will sample it out. Sampling means I am taking a discrete time at t1, suppose I am noting down my amplitude, then I am waiting for n amount of time, and again I am noting down what my amplitude value is, then I am again waiting for the same amount n, and I am noting what my amplitude value is. Like that I am generating this amplitude. So in this case, my amplitude is continuous, but it can be discrete as well. That means it will having a value 0 or it can have a value 1. Like binary values. It can be called as binary values or ternary values or anything that is discrete in nature. So then my amplitude will also be discrete. My time value will also be discrete in that case. So this is how my discrete time signals can be obtained from a continuous time signal. Then how it is represented, we'll see. That is x of n, it is represented by x of n, where n takes the value 0, 1, 2, and so on. It can be represented by nt, x of nt, where n again takes the value 0, 1, 2, and so on. X of n, where n takes the value of 0, 1, 2, and so on. So by these three notation, that is x of n, x of nt, x of n, xn, my continuous time signal is being denoted. Okay. Then we will see what is meant by a discrete time system. So a discrete time system is nothing but a system is nothing but it operates on input signal x of n and it generates an output y of n. So what does this operation mean to be? The operation is a mathematical algorithm. So it undergoes the input signal undergoes mathematical algorithm. This is what my system is, and it will generate an output sequence. Okay, so this is the definition of a discrete time system, that is essentially a mathematical algorithm that takes place on input sequence and produces an output sequence y of n. Okay, now we will see a system should obey certain rules to become near perfect. Okay, so first rule it should follow is a linearity. This is the property that a system should possess. So what does this linearity property means? It should obey the principle of superposition. So what does this mean? It means the system to be linear. That means this is my system, suppose, and it is not having only one input, but it is having many inputs now. To make it simple, we will only consider two input sequence, x1 of n and x2 of n, and it is having a response. The system has a response of h of n, and it generates two output, that is y1 of n and y2 of n. Now how my system will recognize that this y1 of n is related to x1 of n and not on x2 of n, and how my x2 of n is related to y2 of n is related to only x2 of n and not on x1 of n is, first we will consider only one input and we will disconnect all our other input and generate an output signal and denote it by y of n. Okay, then we will the step number 2 is we will consider x2 of n and disconnect my another signal, that is x1 of n, and generate another signal, and then summing it off we will get the total response, the total output of this system. So in general, how we can represent this linearity property is a1 x1 of n plus a2 x2 of n can be written as a1 a1 y1 of n plus a2 y2 of n. So this is how my linearity property will look like. Okay, so for my system to obey linearity, it should perform this superposition theorem, where my a1, a2 are arbitrary constants, Then the next thing my system should obey is time invariant property. So what does this time invariant property means? It means my output is dependent on, suppose this is x of t and it is generating an output y of t, so my the output time is related only to the time of the input. It won't be t minus 1 or t minus 2. So it is not the delayed version of time, it won't depend on that. It will depend on the current time the input is related to. The input is expressed, or an input is expressed. Okay, so where t minus t naught can generate an output of y minus okay, y of t minus t naught. So this is how my time invariant property looks like. Okay, so that means a delay in the input causes the same amount of delay in my output. So this is how my second property look like, and my system should obey this. Then how my output, that is y of n, is related to x of n and impulse response, that is h of n. So symbolically this will look like this. I am subjecting a input, that is x of n, to impulse response h of n, and it is generating an output y of n. So this h of n can be mathematically expressed as convolution sum of minus infinity to infinity. It can be written as h of k x of n minus k. Okay, this is how my output is related to my input and impulse response of the system. So the next thing is stability. So I can say my system is stable when it follows or satisfy a condition. How this mathematically this condition is expressed as k equals to minus infinity to infinity h of k, okay, mod of h of k should be less than infinity. That means the impulse response h of k takes finite duration or stays in finite duration, or it has a finite value, that means. Okay, or if h of k decays towards 0 as my time, that is k, increases or tends to infinity. So then only my system can be said to be stable. So then we will see the another thing is how my system is said to be causal system when say we can take an example of a mobile phone. Okay, this is my screen. Suppose this has some button here, 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 here. So when I'm switching it on, that means my battery is connected to my phone at that point when I'm switch it on, when I switch it on. So till I switch it on, that means the moment of switching can be denoted as 0. So before 0, my signal to this phone was 0. That is x of n is equal to 0 when when n is less than 0. It gives some signal at 0 and greater than 0. It switches it on. So any system is said to be causal in nature. Practically, it is always causal. Okay, so we have discussed all what is meant by a discrete time signal, and we have discussed what is a discrete time system and what all properties a discrete time system should possess to make it a linear time invariant system. Invariant system. So I close my video here. I hope you have enjoyed the lecture, and thank you.